I hope by now that you have downloaded our free simulator program from this website. It will make it much easier to follow the tutorials as we continue. To gain the full benefit of the tutorial, you should use the simulator to experiment with circuits of your own. Here we have a collection of capacitors. Generally, they are recognizable by their plastic covering and their two leads protruding from the bottom. Normally it does not matter which way around they are connected, but the blue capacitor is a polarized capacitor for which orientation does matter. Polarized capacitors typically have a 0 indicating the cathode or negative end. This end should be connected to the negative end of the battery. Up till now the circuits have been static. They are either on or off, and the current either flows at a steady rate or does not flow at all. The capacitor changes that. In this circuit we have a capacitor together with an LED and a resistor. When we switch on, current flows, but rapidly the current diminishes until it stops entirely. We switch off and on again and still no current flows. Clearly the state of the capacitor has changed. The secret of the capacitor is that no current flows through it. Picture the capacitor as two plates. Before the current is switched on, the plates contain trillions of electrons and holes in a random fashion. Many substances contain electrons and holes in this way. Here the electrons are shown as stars and the holes are shown as circles. When current is switched on, the electrons in the upper plate are attracted towards the positive end of the battery. The holes in the lower plate are attracted towards the negative end of the battery. As this process continues, the upper plate becomes more positive and the lower plate becomes more negative. The capacitor itself becomes like a small battery with the positive end at the top and the negative end at the bottom. The capacitor therefore begins to oppose the voltage of the main battery. Current slows down. The process continues until the voltage of the capacitor equals the voltage of the battery, and so completely opposes it. At this point, current stops. If current is switched off, the capacitor continues to hold its voltage, because there is no way for the holes and electrons to jump from one plate to the other. If the current is switched on again, no current will flow, because the capacitor continues to oppose the battery. Let us demonstrate this with an example. When we turn on switch 1, LED 1 flashes. Now we believe the capacitor has been fully charged while LED 1 was lit. So the capacitor has a charge equal to that of the battery. Switch off switch 1, the capacitor retains its charge. Switch on switch 2. This time LED 2 flashes. This is because the capacitor has discharged through LED 2. The capacitor has no charge now, so we can repeat the process because there is no charge opposing the battery. Now let us repeat the process using an oscilloscope instead of an LED. We have set this oscilloscope to measure voltage with a base of 0 volts and a range of 10 volts. The oscilloscope is positioned to show the voltage of the capacitor. Turning on switch 1 causes the voltage in the capacitor to rise to 9 volts. When we turn off switch 1, the voltage remains steady at 9 volts. Now we turn on switch 2 and watch the capacitor discharge until its voltage is 0. We can repeat the process as before. Here are two circuits with identical capacitors and resistors. What differs is that the battery on the right is only 0.9 volts. The oscilloscope on the right has been adjusted to show a voltage range of 1 volt. The circuits are on, so we see what happens when we turn on the simulator. It is apparent that each capacitor reaches its peak voltage in the same time. In short, the time taken for a capacitor to reach the voltage of the battery is independent of the voltage of the battery. Now we show two similar circuits, but the oscilloscope on the right is showing current instead of voltage. Remember that to measure current, the current must pass through the oscilloscope. The two circuits are on, and when we turn on the simulator, we see the voltage curve on the left and the current curve on the right. Notice that they are the inverse of each other. We will show that again. We need to introduce a measure of electrical energy. Just as we may have a bucket of water, we now have a bucket of electrical energy called a coulomb. This is the electrical energy equivalent of 1 ampere flowing for 1 second. Equally, it could be the electrical energy equivalent of half an ampere flowing for 2 seconds. The top two graphs show this. Suppose we have a certain size of capacitor with an external battery of 1 volt and resistor of 1 ohm. We know that the initial current will be 1 amp, but the current will diminish and finally stop. This current curve is shown in the third graph. If the volume of current equals the volume of current in the top graphs, then the electrical energy absorbed is also 1 coulomb. Recall the size of this capacitor 1 farad. More formally, 1 farad can be described as the capacitance which stores a 1 coulomb charge across a voltage of 1 volt. Looking at the distinctive shapes of the voltage and current curves, we can show mathematically that a 1 farad capacitor under control of a 1 ohm resistor will reach 63% of its final voltage in 1 second. In 2 seconds it will reach 86% and so on until it reaches full capacitance. A farad has been named after Michael Faraday, the 19th century English scientist. You may also want to look up Alessandro Volta, Georg Ohm, André-Marie Ampère, and Charles Augustin de Coulomb. In electrical circuits, 1 farad is rather a large unit, so smaller capacitances are defined as follows. 1 millifarad is 1/1000th of a farad. 1 microfarad is 1/1000th of a millifarad. 1 nanofarad is 1/1000th of a microfarad. And 1 picofarad is 1/1000th of a nanofarad. Notice again the special mu character for the micro symbol. On the left we have a 1 millifarad capacitor with a 100 ohm resistor. On the right the capacitor is 10 millifarads while the resistor is 10 ohms. The two circuits produce the identical voltage curve. This tells us that two circuits where the products of resistance and capacitance are the same will have the same voltage curve. Try various resistances and capacitances yourself to verify this point. This leads us to a useful formula. The time taken to charge the capacitor is a function of the resistance and capacitance. In particular, we know that with a 1 ohm resistor, a 1 farad capacitor will reach 63% of its capacitance in 1 second. So we can generalize this formula. T equals Rf, where T equals time in seconds taken to reach 63% of capacitance. R equals resistance in ohms, F equals capacitance in farads. Also, if T is the time taken to reach 63% of the charge, then twice T is the time taken to reach 86% of the charge, and so on. There are two further matters to look into concerning capacitors. The first is, what happens if we have capacitors in parallel? Two capacitors would have double the plate size of a single capacitor. So it is logical that with capacitors in parallel we can add the capacitances together to find the total capacitance. You can verify this with your own tests. Finally, what about capacitors in series? We see that two capacitors with double the capacitance of the single capacitor, when placed in series, are equivalent to the single capacitor. The formula for capacitors in parallel is similar to that of resistors in series. It turns out that the formula for capacitors in series is similar to that of resistors in parallel. Here then are the formulae for capacitors in parallel and in series. That concludes part 3 of this tutorial. Part 4 will be investigating the transistor.